Hello everyone, this is Revant from CSM Section C. Today I am going to explain about travel salesman problem. Let's start with some introduction. Title and introduction. Title is Traveling Salesman's Salesperson Problem. A survey of modern techniques. Subtitle Conquering NP hardness for real world logistics key concepts. Definition Find the shortest tour visiting every city exactly once and returning to the start. NP hardness, no, NP hardness, no now polynomial time algorithms exist for the optimal solution. The number of possible routes is n minus 1 by n minus 1 factorial by 2. The solution divide exact algorithms. Optimal sure, optimal slow versus heuristic and meta heuristic. Near optimal or fast. Now we can go into next slide. Exact methods for proof of optimality. Topic is branch and cut and integer programming description. The methods guarantee the optimal solution but are only practical for problems up to a few thousand cities. Core technique. The Cons code solver integer linear programming, shortly called as ILP. Formulate the TSP as an ILP problem. Cutting plain method starts with a relaxed problem, ignoring the integer constraint, and interleative adds cuts valid inequalities constraints like Stuber subtour elimination to tighten the solution space. Branch and bound. When culls are insufficient, the problem is divided, branched into subproblems, and lower bounds are used to prune unpromising branches. Significance used to set the world record for largest solved TSP instance. Example 85900 cities. Now we are going to next slide. Classic approximation algorithms. Topic is Christophides algorithm description. A historical benchmark. This is a polynomial time algorithm with a theory approximation guarantee. Algorithm for metric TSP. 1. Find a minimum spanning tree MST for the cities. Second one, find a minimum weight perfect matching on the vertices with odd degrees. In the MST, third one, combine the MST and the matching edges to form an Eulerian graph. The fourth one, find an Eulerian circuit and convert it to a Hamilton cycle. By shortcutting revisited nodes guarantee, the resulting tour length is at most 1.5 times. Next slide. High performance local search. Lin Kagan heuristic, simply called as LKH. The LKH family. LKH1, LKH2, LKH3. Description. The most effectively and widely used heuristic for find near optimal solution for very large symmetric TSP. Instance, millions of cities, core idea. Vermaat moves KOPT move, a local optimization technique where K edges are removed from the current tour and K new edges are added to form a new shorter tour. LKH advantage uses a variable K not fixed like 2 OPT or 3 OPT and allows for temporary cost increases to escape local optima performance. Routinely finds the optimal or an extremely close solution in practical time. LS3 extends this to TSP variants like multiple TSP and constraint TSP. Now we are going to next slide. Bio-inspired meta-heuristics and colony optimization, simply called as ACO. Topic is and colony optimization ACO description. A probabilistic technique inspired by the foraging behavior of real ants which deposit pheromones to mark good paths. How it works? First, initialization. Artificial ants are placed on cities. Second one, tour construction. Ants move city to city, choosing the next city based on combination of pheromone level, expollination, and edge distance exploration. Third, pheromone update. After all ants complete a tour, pheromones evaporate and are reinforced on the shortest paths found. Positive feedback. Application. Excellent for dynamic and complex optimization problems, often combined with a local research. Example a short 2 OPT. To improve the quality of the ants tours before pheromone update. We are going to next slide. Bio-inspiring meta-heuristic genetic algorithm, simply called as GA. Topic: Genetic algorithms. Description: A search heuristic based on the process of natural selection and evolution. Key components: Population: A set of initial random tours, solutions, individuals. Fitness function: Evaluates the tour quality. The shorter the tour, the higher the fitness. Selection: Better tour, high fitness are chosen to be parents. Crossover recombination. Parent tours are combined to create offspring tours using order crossover or partial mapped crossover. Mutation. Random small changes swapping two cities are introduced to main diversity and prevent stagnation. Strength. Highly effective for searching a vast solution space and very easily adapted to constrained TSP variants. Now we are move to the next slide. Reinforcement learning, simply called as RL approaches. Topic: Reinforcement learning or DRL for TSP description. A modern data-driven approach where an agent neural network learns to construct a highly quality tour by interacting with the problem environment. Model architecture example. Model often a pointer network or graph neural network. Action. Selecting the next city to visit. Reward. A negative value to final tour length. The agent is penalized for longer tours. Training. The agent is trained on the thousands of sample TSP instances to learn a policy that generalizes well to new unseen instance. Advantage: potentially for fast inference once trained and ability to generalize solution strategies across different problems sizes. Still largely a research area compared to LKH cons code. Hybrid and adaptive algorithms. Combined strengths for superior performance description. State 1 the art results are often achieved by combining multiple techniques. First one, Hybrid meta-heuristics, GA plus LKH. GA performs global exposure to find promising regions of the solution space. LKH performs local exploration, fast deep search to quickly refine tools found by the GA. Second one, anytime algorithms. Algorithms designed to find a good solution quickly and then continually improve it over time. Crucial for real-time logistics where a decent solution is needed immediately but a better solution is valuable. If found moments later, the automated algorithm selection using the machine learning to predict the best algorithm for a specific problem instance based on its characteristics, city distribution, real world applications, and variants. Behind the symmetric TSP description, the TSP models numerous real world optimization problems often with added complexity, key real world applications, vehicle routing problems, VRP, multiple sales powerful vehicles, capacity constraints, time windows, VRP with time windows, VRTTW, logistics and delivery, optimizing last mile delivery routes, Amazon UPS, manufacturing, optimizing the path of a machine, drilling holes in a circuit board, laser cutting, ordering DNA fragments, modern solvers, commercial and open source solvers like Google or tools and Concorde are heavily utilized to implement these techniques for partial logistics. Now we are going to end this one with conclusion, future direction. The TSP challenges continuous modern techniques, recap, extract, branch and cut for proven optimality on modern scale. Approximately Christophites, theoretical $1.5 bond, heuristic LM, Keinarg heuristic LKH for near optimal fast solutions on large scale. Meta heuristics, ACO, GA for robust solution in complex constrained environments. Future directions. One, quantum computing. Exploring quantum algorithms like quantum annealing for exponential speed up on NP hard problems. Second one, deep learning. Improve DRL models to match or exceed the quality of LKH. Third one, better lower bounds. Discovering tighter theoretical bounds for approximation algorithms. Key takeaway. The balance between speed, solution quality, and proof of optimality drives ongoing research. Okay, bye. Okay, guys. I hope you enjoy this session. Thank you for everything.